We'll be talking to us today about integrated modulators using Coherent Perfect Absorption. And let's get started, and I'm going to give you a 2-minute warning.
Okay. Thank you, Steph. So my name is Jacob Rothenberg. I'm with the Photonic Devices Lab at Columbia University. And I'm going to talk about a project I've been working on since I came to Columbia a couple of years ago, and sort of been a whole lab effort between these people, but sort of got some new results that I'd like to share with you guys. So Coherent Perfect Absorption is kind of a new phenomenon that was first termed about 10 years ago by Douglas Stone at Yale. And at the time, it kind of got some popularity because they called it the anti-laser, because if you take a laser and you replace the gain material with a lossy material instead, the time reverse solution to the lasing phenomenon actually becomes the coherent perfect absorption phenomenon. So if you imagine a laser, you start with no light, and then as time goes on, in the gain material, you output laser light. You can think of coherent perfect absorption where you put in light, and based on the different properties, you can actually absorb all the light within the material, or you can have a state where all the light is transmitted to the material. But more simply, it's really just superposition plus critical coupling. So if you think about a resonator in a simple sense, if you have two inputs and the two waves have a phase difference delta phi, and then you give some coupling loss between the inputs and the resonator, and then the resonator itself has some internal loss. It turns out, which I'll show in a second, that the output power as well as the on resonance power loss, so the amount of power absorbed within the resonator, can vary between 0 and 1. So based on this delta phi, so you can have a state here where all of the light is being absorbed within the resonator and nothing comes out, and then you shift the delta phi by pi, and then you move to a state where all the light is being output and nothing is being absorbed in the resonator. And here is an example that group gave when they came out with this theory. So they basically just took a Mach Zehnder interferometer and stuck a little silicon wafer in there. And here's a little cartoon that makes it easier. So here's the two inputs, here's the resonator, and here's your theoretical and experimental data. And they found that at pi phase difference, nothing came out. Well, very little came out. And then at 0 and 2 pi, you got a much higher. And I believe this was, they said, 2 orders of magnitude difference between the on and off state. So this was the first real physical demonstration. And our lab makes silicon photonic devices, and we sort of saw that this coherent perfect loss phenomenon kind of has a natural, it kind of naturally behaves sort of like a switch. And a lot of photonic devices are, in essence, switches, no matter what they do. And I saw a lot of people's posters are a lot more physicsy, but if you don't know, a silicon ring resonator has kind of become the sort of the building block of silicon photonics. It's basically just a ring, and if you have a silicon waveguide that you put near the ring, the evanescent wave will couple into the ring based on the resonance of the silicon ring resonator. So if you have a wavelength division multiplex signal with a lot of different wavelengths, you can build the ring such that only one wavelength will couple out, and then that's how they do a lot of routing and all optical switching, and a lot of modulators are built this way now. So you turn it on and off based on voltage, and it has very low power consumption, and it's relatively fast and compact. So we used temporal coupled mode theory, and without going too far into it, we found that the power loss actually has a cosine squared transfer function, but the most important thing to note is that there's two conditions that you can achieve with coherent perfect loss. One is that it has to be on resonance of the ring resonator itself. The second is critical coupling. So this loss rate has to be perfectly matched to the internal loss rate of the resonator. So if you don't have, if they're not perfectly critically coupled, it won't go to 0 and it won't go to 1. So see, like we know cosine squared has a 0 and it also has a 1. So it can vary between the input power and 0. So you can see that here. So we can go from 0 to 1, and then we did some finite difference time domain calculations, and we showed that it actually does work in theory. So you have this off state where delta phi equals 0, so PT equals 0, and you can see you input these two waves, and all the light becomes absorbed in the cavity, and then you put these two waves offset by delta phi equals pi, and then it completely just passes through. So in modulator terms, this is like switching between a notch filter and an all-pass filter. So in one case, it will pass through, it will absorb only at the resonant wavelength of the resonator, and then in the other case, it'll pass through. So we were able to verify with simulation that it could work in that way. The next step that I've been working on for the past year has been to actually fabricate this device. And our group earlier had done some work with ion implanted silicon, which if you don't know, silicon isn't very, it's not a great optical material at telecom wavelengths, but there's been some research that says if you ion implant silicon, you create these defect states, which basically shift the band gap so that silicon becomes more and an absorber at telecom wavelengths. And you can see here, these are our ion implanted regions, this orange area. And so the two curved areas are the ion implanted regions. And this is one input waveguide, and this is the other input waveguide. And this is where the coupling happens, and you can't really see the gap. There's a little gap right there. And the gap actually determines this gamma C, and the gamma I is determined by the absorptive coefficient of the ion implanted silicon. And this is a little schematic to show you. So we use these dimensions, just 500 nanometers, to ensure we're in single mode operation. And we used this size, so our free spectral range was about 4 nanometers, so our resonance are about 4 nanometers apart. So we could show that it could do WDM, things like that. This is our setup that we used to test this. We didn't have, so the two waveguides coupled in, we actually coupled them in separately, and we used fibers to do an off-chip delay. And so we use like a lithium niobate phase modulator to impart a delta phi compared to the other, and then we have a delay line, which we got pretty far into interferometry today, but it's basically just to make sure we see the fringes. And it actually, our next device, we want to do an on-chip delay, because off-chip delay, we have all these these just random phase fluctuations in the fiber that sort of limit the speed which we can switch at. So this is the first data that we got from this device very recently. And so if you start on the right, this is at 1552.1, so it's on resonance. And we basically take the voltage source and we apply a linear ramp, which for the lithium niobate is basically linearly shifting the delta phi compared to the other arm. And we saw the sine squared behavior that we saw in our finest different time domain calculations. So we were able to verify that. And then we moved to wavelength sweeps where we swept over, we used an OSA to sweep over one of the resonances. So we would sweep over the resonance at V equals 0, and then we would immediately switch to V pi. So we would switch like from here to here, and then we would do a scan again, and we were able to see that we were able to switch basically from like here, which represents this point in the curve, and then to here, which represents this point in the curve. And then if you look at the numbers, this gap between the two states matches this this extinction of the sine squared resonance. So our further work is to do photocurrent measurements. So if you remember from our device, there's these aluminum contacts right here. So remember we have PT and PL. So we've been looking at PA and B, so the output, but we can also look at PL, which when the ion implanted regions create the loss, we can actually quantify that loss by collecting those photo-generated carriers that are generated from the lossy material. And we're working on that now. The second is to maximize the extinction ratio. So if you remember, to get coherent perfect loss, we need the loss rate to be critically coupled to the coupling rate. And as I said before, this like internal coupling rate is based on the loss rate of the ion implanted silicon, which has kind of it's not very exact based on fabrication. So we created a bunch of different devices, and we're with different coupling gaps, and we're trying to match the one that perfectly matches the loss rate that we have with the current device. So ideally, we would want this line to be flat instead of still dip, and we've actually found a couple more devices that flatten out and have more like 15 dB extinction instead of like this 8 dB extinction that you see here. So, and you might be wondering why this matters. So I think I mentioned this, we want to do on-chip phase shifter and on-chip receivers, just basically showing, the more you can show that everything is integrated on-chip, the better. But our long-term goal is to demonstrate that it can have functionality in coherent communications. Okay. So what that means is for instance, DPSK is a modulation scheme called differential phase Q shifting, and it has favorable qualities like better signal to noise ratio over on-off gain. And basically what it does is it encodes ones and zeros by having phase shifts from the subsequent bit to the next bit. So one bit will have a phase of 0, and then if you want to have a 1, the next bit will have a phase of pi. And then if you want to have a 0, it'll have the same phase. So we've been doing work, and we just were able to do some finite difference time domain, and showed that if we delay one bit from the other, then interfere them in this ring, we can actually back out amplitude modulated signal for a direct detection. And then once we can show this on a single device, we want to expand it to a full, more systems level solution where we have many of these devices lined up, and we can take like a fiber with many signals and sort of multiplex or demultiplex them together in a full, more systems level solution. So just summary, we thought about CPA, and we thought about how we could design a novel device for it, and we fabricated the device, and we've started to demonstrate that it shows CPA, and we're excited about possibly showing it in further applications.
So let's look at your speaker. Are there any questions?
Do you have any estimate of how much your phase noise will be reduced by going to didn't look that bad.
Yeah, that's a good question. It didn't look bad, but I also kind of, I didn't not that I hit it, but it's like, so this was like one plot is like an average over a bunch of v equals zeros, and then this other plot's of an average of a bunch of v pi's. So it's like if you look at only one, it kind of like it wiggles around, and then if you look at the other one, it wiggles around, and like if you want to actually put data on it, it has to be like very stable. So like the bit error rate needs to be like 10 to the negative 12, whereas we haven't done a bit error rate on this, but it would probably be like 1 to the negative 3, if that. So, but any like any real device that's like uses data, like a Mach Center or something, uses on-chip delay. So I'm pretty sure a lot of it's due to that.
You had sort of discussed like the fabrication process and how that needs to be good. Do you know in terms of thermal effects with the resonance of your ring resonator, what effect that has in terms of the coherent perfect absorption conditions? Like how flexible is your device? Like if you use it in a real world with temperature fluctuations or something.
Yeah. Well, one of the reasons we used ion implanted silicon is because we wanted it to be an all silicon device, so it could be compatible in like a CMOS process. Okay. But another reason we used ion implanted silicon is because we had already been doing work in it, so we were kind of familiar with it. Okay. But there's no reason why we couldn't use another like more popular like germanium or something that's more popular used for photodetectors that's really well known. Because as I said, like the fabrication for this is still like, it's not like this gamma I, the internal loss, it's basically quoted as like a range right now. Like, so I guess your answer is like, yeah, it's not ideal because it's still kind of more in the experimental phase. Like there's no commercial devices with ion implanted silicon. But if we wanted to make a device that maybe was the best possible device, we probably could have used a different material. But we think this is a promising material in the future just because a lot of devices have really good properties, but no one would ever use them in a silicon photonic chip because it would you can't use it on the CMOS process. Okay. So.